Hi everyone, in this video we are going to study about the stability analysis of the feedback circuit. So we have seen a lot of negative feedback circuit, we have also seen positive feedback circuit. Negative feedback circuit we saw in op-amps as well, in MOSFETs as well. Positive feedback circuit we saw in op-amps when we were studying about oscillators, right? So now we are going to talk about the stability of that. We got to know that the circuit in positive feedback is not stable if your A beta is greater than or equals to 1 and your total phase shift is 0 degree or 360 degree. Basically, if total phase shift is 0 degree 360 degree, that means the system is in positive feedback only, and if the loop gain is greater than or equals to 1, then the system will be oscillatory. That we have already seen in the concept of oscillator. This was around 2 hours of video. There we studied everything about oscillations. So first watch that video, then only come here, then only see the analysis of these oscillators. Okay, so what we studied there, now we are going to study about feedback circuit, but just revisiting the concept of oscillations. What it was saying, that at a particular frequency omega naught, if our phase shift around the loop is 0 degree or 360 degree, and if my gain is greater than or equals to 1, then my system will be oscillatory. So oscillatory, or I can say unstable. Here it will also be oscillatory only, but the oscillations will be sustained, right? Sustained oscillations. Sustained oscillation means the oscillations will be same. In case of A beta greater than 1, the oscillations will be like this. It will keep on increasing, right? And in case of A beta equals to 1, the oscillations will be sustained. Same oscillations will be there. And in case of A beta less than 1, the oscillations will die down, right? So here sustained oscillations, and even if there is sustained oscillations, that means still the system is unstable only. And if A beta is less than 1, that means oscillations die down. Oscillations die down. And if oscillations are dying down, that means system is stable. So our target is, when I am designing a circuit, our target would be to take A beta should be less than 1 at a particular frequency where your phase shift is 0 degree or 360 degree in case of positive feedback. I will again repeat the line. Let's just say I have designed a circuit that is in the positive feedback. The circuit is in positive feedback. So I will make sure that at the frequency when my phase shift is 0 degree, at that time my loop gain should be less than 1. As a designer, I will take care of this thing. We will see examples, it will be more clear to you. But when can a negative system will be unstable? Negative feedback system will be unstable. At what frequency or at what phase shift the negative feedback can be unstable? We studied that negative feedback system is stable, right? What is the transfer function? A upon 1 plus A beta. Now tell me one thing, from here to here there is 0 degree phase shift, right? From here to here again there is 0 degree phase shift. But from here to here, what is the phase shift? This is 0 degree, 0 degree. From here to here, negative sign will go, negative sign will carry on. V in I have shorted, whatever the output part is coming, if this was beta V naught, what will come here? Minus beta V naught, right? This is V naught, this part will be beta V naught. And this part will be minus beta V naught, right? Minus beta V naught. Minus beta V naught. So basically from here to here there is 180 degree phase shift. Now what if my system is such that my A beta is providing me 180 degree phase shift? If my A beta is providing me 180 degree phase shift, then tell me what will be the total phase shift? A beta combined is providing me 180 degree phase shift from here to here. A beta combined is providing me 180 degree phase shift. So 180 degree phase shift from A beta will come, and 180 degree phase shift from here because of this negative sign, because this is a negative feedback system. So if A beta provides me 180 degree phase shift, then my total phase shift will be 0 degree, or you can say 360 degree, right? Because 180 we are getting from here, 180 we will get from here. So total phase shift will be 0 degree or 360 degree, then my system can become unstable, right? If my total phase shift is 0 degree or 360 degree and my A beta is greater than 1, then my system can become unstable. So always we need to make sure what my gain A is. If my gain A is also providing me some phase shift, or the feedback factor beta is providing me some phase shift, then it can make my system unstable even in the negative feedback. Are you able to process this statement? It's not necessary that your negative feedback system will always be stable. If your forward gain and the feedback factor combined is giving you a phase shift of 180 degree phase shift, then it can become unstable considering the loop gain, if loop gain is greater than 1. So we will see the examples one by one. Okay, so let's just remove this part, this is of no use. So basically here we were having 180 degree phase shift in the loop. As of now we were having 180 degree phase shift in the loop. So A beta is giving you 0 degree phase shift. So let's just not write it, just let's just write this much only. So for a negative feedback system, this is our transfer function, and at some frequency, if your A beta is greater than or equals to 1 and the phase shift provided by the loop is 180 degree phase shift, then the system will oscillate. Are you understanding this concept? Okay, so again I will draw this diagram. I will draw this diagram here. So let's just say it is providing you some x degree phase shift, this is providing you some x degree phase shift, this is providing you some y degree phase shift. So total phase shift is x degree plus y degree plus 180 degree. This is the total phase shift, right? 180 degree is already there, and if x plus y is 180 degree, x plus y is 180 degree, then total phase shift will be 360 degree. This is your total phase shift, and if this is your total phase shift, then the system would become unstable, considering the fact that at A beta greater than 1, at that particular frequency, my magnitude is greater than or equals to 1. If my magnitude is less than 1, then the system will still be stable. What I am saying, if my phase shift is 360 degree, my phase shift is 0 degree, but at that time my loop gain is less than 1, then still the system will be stable only. Let's see more example. Let's go more into the depth of stability analysis. So first we will analyze second order system. In this complete video we will analyze first order system as well, second order as well, and third order as well. Okay, all three systems we will analyze. First we will analyze second order. You will understand why we are analyzing second order first. Okay, so yeah, let's just analyze the second order system. So this is the open loop, this is open loop, right? There is no feedback present. How I can make a feedback? Let's just say from here I make a potential divider and provide some feedback to the input side, So this will be my feedback system. Basically the thing is, currently this is my system. There would be a gain A, better I should write A of S. So because there will be frequency content as well. So A of S, there will be a gain A, there will be this output, this is your V in. That's it. I can provide some feedback, right? I can provide feedback any day. I will get some beta and provide it back to the input. I can provide feedback any day, but this is the current scene. So with the help of open loop, can we comment on the stability? This is what we are going to check now. Okay. So this will be our transfer function GM. This you can write down, right? Very simple. In the frequency response we have studied it. GM into GM1 into GM2 into R1 R2 upon poles. Pole location are these, right? These are the pole location. You can draw the Bode plot as well, and you can draw the phase plot as well. But phase plot you might have forgot, so I will tell how to make the phase plot. This is our transfer function. Now we are making the phase plot, right? And one condition I have taken here is that R1 C1 is very greater than R2 C2. So first, which one will be the first pole? Omega P1 would be 1 by R1 C1, because 1 by R1 C1 will be lesser, right? If this is greater, then 1 by R1 C1 will be lesser, and this is your omega P2. So it will occur later on. First this will occur. So now we need to draw, what we need to draw? We need to draw phase plot. Bode plot you can draw. How will the Bode plot look like? Two poles are there, then another roll-off will be there. So this is how Bode plot will look like. But let's just draw the phase plot. You might have forgot how to draw the phase plot. So let's understand how to draw the phase plot. And I am not sure if I have taught you about the phase plot. I don't remember it actually. So let's study it from the scratch. We are going to study how to draw the phase plot. So how we will draw the phase plot? So can you write down the phase plot of this one? Can you write down the phase of this one? What is the phase of this? That would be minus tan inverse omega R1 C1 minus tan inverse omega R2 C2, right? First, let's the phase plot of only minus tan inverse omega R1 C1. What if I say that omega is very lesser than 1 by r1 c1. Omega is very small value. If omega is very small value, that means this would be nearly approximate to 0, and tan inverse 0 is 0 degree. So tan times lesser than 1 by r1 c1. 1 by r1 c1 will be your what? Will be your pole. So tan times lesser than this. That means 1 by tan r1 c1. At that time, till this time, you can take your phase to be 0, because these values will be lesser than 1 by these values. These value will be lesser than 1 by tan r1 c1. So till that time, you can take your phase to be 0 degree. At 1 by r1 c1, what will be your phase? At 1 by r1 c1, tan inverse 1 by r1 c1. Omega is equals to 1 by r1 c1. 1 by r1 c1. At that time, your phase will be minus tan inverse 1, and that would be equals to minus 45 degree, right? So at that time, your phase will be minus 45 degree. Minus 45 degree. And for tan times larger, let's just say I am saying that my omega is tan times larger than this one. My omega is tan by r1 c1. This is my omega. So calculate it in your calculator, that what value you will get. My omega is tan by r1 c1. So minus tan inverse tan. It will be somewhat 89.9 degree somewhat. So it will be minus of 89.9 degree. So approximately it can be taken as minus 90 degree. Are you getting this point? So at 10 times more than this, you will get, at 10 times more than this, you will get minus 90 degree. And after that, it will always remain at minus 90 degree, because minus tan inverse infinity, it will be minus 90 degree only, no? So you cannot get more phase shift than that. Minus 90 degree is your maximum phase shift. So basically, it will start like this. For very lower value, it will stay lower. This is just an approximation method given by Bode. So this is how he told us to plot. So he said that you say at the pole you will get 45 degree phase shift, right? And after that, at 10 times more frequency, you will get minus 90 degree phase shift, and at 10 times less frequency, you are getting 0 degree phase shift. So this is how you can draw the phase plot. Okay, so this we have drawn for this much. So this is how we draw the Bode plot for only this one. This is not the complete one. We will draw for tan inverse omega r2 c2 as well. So let's draw for tan inverse omega r2 c2. So basically here I can show the angles as well. This was 0 degree, because angle is also very important part, and this was 90 degree. And this was 45 degree. This was minus 45 degree, and this was minus 90 degree. Okay, and what will be the slope? Can you tell me? 45 degree per minus 45 degree per decade. Do you agree to this point? If the increase in your frequency is 10 times, then it is going down by minus 45 degree. If the increase in frequency is 10 times, it is going down by minus 45 degree. That means the slope is minus 45 degree per decade. In Bode plot, what we used to do? We used to write the slope is minus 20 dB per decade. That means if the increase in frequency is 10 times, that means it is going down by minus 20 dB. Right? If the increase in frequency is 10 times, it is going down by minus 20 dB. So similarly, if the increase in frequency is 10 times, it is going down by minus 45 degree. You can see here as well, from 0 to minus 45 degree, 10 times increase. From here as well, 0 to minus 45 to minus 90 degree, 10 times increase. Same goes for this one, exactly the same. First you will see your pole, then 10 times lesser, and then 10 times more. 10 times lesser, 10 times more. Now you just need to add these two graphs. Just add both of them. Right? So what we are doing, what we have said, what is the assumption? That 1 by R1C1 is very, very lesser than 1 by R2C2, right? So all these values will occur very near to 0, right? All these values will occur very early and these will come later on. Basically 1 by 10 R1C1, 1 by R1C1 and 10 by R1C1 will occur very early, and then later on these 1 by 10 R2C2, 1 by R2C2 and 10 by R2C2 will come, because this is very, very lesser. This is the assumption we have made. So how will your total plot look like? So from 0 it will start, okay, it will keep on going till 10 by R1C1 we are not even getting this one. So before that, from this side you are getting 0 degree. Before 10 by R1C1, from this side you are getting 0 degree. So from here you are getting 0 degree only, and from here you are getting this much. So first, how will our total body plot look like? So first it will follow the complete one, right? And then it will stay at 90 degree. Now this one will come. Are you getting this point? Now these values will come. So now here 1 by 10 R2C2 will come. Till this point, all these values have come. You are just adding up, nothing else, just a simple addition of two graphs. Now these values will come. You are already having 90 degree here, 90 degree plus 0. After that, this slope you are having, So at this point, what you will have? Minus 90, minus 45. What you will have? Here you are already having minus 90. Minus 90 is going on. It will go till infinity, okay? Minus 90 will go till infinity. Till infinity it is going. So minus 90 minus 45. So it would be minus 135. Minus 135. And then at this point, what you will have? Minus 90, this one, and minus 90 already. Then it will be minus 180 till the end. Minus 180 till the end. So I have drawn the complete graph already. You will be able to understand it. This is the complete graph. This was the body plot, which is very easy. I hope you all have studied it. This is the body plot and this is the complete graph. 1 by 10 by R1C1, till this point nothing has occurred. Now this 1 by 10 R1C1 started coming. So minus 90 and then these negative angle will add up. So these negative angles are getting add up. And at this 10 by R1C1, you will have minus 90 degree here and minus 90 degree here. So this will be total minus 180 degree. So this is how you draw a phase plot. Okay. I hope it is clear to you. For a second order system, you have drawn a phase plot now. Okay. Now let's just see one thing. So at 10 by R2C2, you are having your phase shift approximately around minus 180 degree. Okay, this was the forward gain. Forward gain. Now what I am assuming is that my feedback is not providing me any phase shift, or neither it is giving me any reduction in the gain. Basically, I am assuming beta is equals to 1. This is what I am assuming. Beta is equals to 1. Right? Since it is a negative feedback system, that means certainly minus 180 degree is already there. And I am assuming that from A beta, I am getting nothing. Are you able to understand this point? Look, A is our some A of S, our forward gain. Forward gain is some DC gain divided by two poles. Some DC gain divided by two poles. So this is giving us some phase shift. Forward gain is giving a phase shift. I have assumed my beta S to be equals to 1 only. It is not giving me any phase shift, neither it is giving me any reduction. Okay. This is what I have assumed. Now, at 10 by R2C2, here I am getting minus 180 degree phase shift. So at this point, 10 by R2C2, what is your loop gain? What will be your loop gain? At this point, your loop gain is less than 1. Say yes or no. And if your loop gain is less than 1, that means this system is stable. Did you understand this point or not? When this phase shift was minus 180 degree, at that time your loop gain is less than 1. That means your system is stable. We are considering only the phase shift we are getting from the forward gain. From the feedback path, in feedback path basically we are going to connect a resistance only, right? in the feedback path, we are going to connect a resistor divider. This will be your V naught, this will be your R1, R2, and this will be fed back to the input. This would be your beta V naught. Although the beta value will be lesser than 1, but here we are considering the beta value is 1. If it is lesser than 1, then A beta, this will shift just a bit downward. It will just shift downward. The plot will just shift downward for A beta. For A beta. So better I should write A beta here. A beta. This is the magnitude of A beta and this is the angle of A beta. Here I am not writing GM1, GM2, R1, R2. Why I am not writing this? Because it will be multiplied with beta as well. So it may happen that the gain may reduce. So even if the gain is reducing, this plot will go down, right? If beta is 1 by 2, will there be any change in this phase plot? If beta is half, will there be any change in the phase plot? No, because phase plot will not depend on the magnitude. Phase plot will not depend on the magnitude. Even if the magnitude is 1 or 2, the phase will not depend on that. Phase will just depend on these terms. So what we are drawing? We are drawing A beta here, not A. This is your A beta. Considering beta is equals to 1, this is what I have considered. If beta can be half as well, then only this graph will be changed. Beta can never be greater than 1, this is for sure, right? Beta would be lesser than or equals to 1. So this is the worst case, right? This is the worst case when beta is equals to 1. If beta is half, then this will shift downward only. And if this is shifting downward, that means your A beta is going more lesser than 1. And if your A beta is very lesser than 1, then it is useful for us, right? Because if A beta is very lesser than 1, that means we are moving towards stability. If A beta is very high, that means our system can be unstable. So what we got to know that at this frequency, when our phase shift is minus 180 degree, at that time my gain is lesser than 1 or my gain is less than 0 dB, because this is 0 dB, right? Here gain is equals to 1 or 0 dB or 0 dB. Body plot, basics of body plot you should know, which I have already taught in the course. So here the gain is 0 dB or 1, you can say. This could be 0 dB or 1. In decimal it is 1 and here the gain is 0 dB. So below that we are going. So my gain is lesser than 1. That means my system is unstable. Now people will have one doubt that, sir, you don't know the value of this gain. You don't know the value of this gain. Let's just say the gain was very, very less. The gain would have been, the gain would have been very, very less. Very less. And then there would be very quick roll off, right? So here only, at this frequency only, you will get to know that the system is stable. At minus 180 degree, the gain will be very, very lesser than 1. That means the system will be stable. Yeah, that's what I am saying. I am taking the worst case. I am taking the worst case. And now some people will have the doubt that, sir, what if the gain is very, very high? What if the gain is very, very high? So roll off will be very, very less. Let's just say roll off will be something like this. Roll off will be something like this. So at this frequency, you can have the gain greater than 1 as well. Are you understanding the doubt? Some people can have the doubt that, sir, gain is very, very high. So roll off will be very slow, right? Roll off will be very late. This is minus 20 dB roll off and another minus 20 dB roll off will come. So it may happen that at this particular frequency, you are having a gain greater than 1. But Bode plot is an approximate plot. Actually, minus 180 degree phase shift you will get at omega equals to infinity. Actually, minus 180 degree phase shift you are going to get at omega equals to infinity, not at omega equals to this frequency. So minus 180 degree phase shift will come at omega equals to infinity. So you have to check at omega equals to infinity. Are you getting this point? You have to check at omega equals to infinity, because minus 180 degree phase shift will come at infinity. So at infinity, certainly the gain will be lesser than 1. Say yes or no. At omega equals to infinity, minus 180 degree phase shift will come. This is the approximate plot. We are saying that at 10 by R2C2, our phase shift will be minus 180 degree. But this is not the exact plot. As per the exact plot, this is the white one which you can see. This is the exact plot. As per the exact plot, at omega equals to infinity, you will get minus 180 degree phase shift. Here you can put as well. If you put omega equals to infinity, then minus 90 and minus 90, then minus 180 degree phase shift. So at omega equals to infinity, certainly there will be greater roll off at omega goes to minus at omega goes to infinity, roll off, and then it will keep on rolling off. So certainly at omega goes to infinity, the gain would be lesser than 1 only. So it is 100% sure that this system will be stable. Are you getting this point? Okay. Unless your forward path is providing you any phase shift, basically this forward path is providing me this phase shift, and this is the body plot. As per this body plot, this system will be 100% stable. So what kind of questions can be asked in your interview? During my internship, this question was asked to me. Basically, they will draw these two curves and they will ask you whether the system is stable or not, and they will ask you why is it so. If it is stable, why it is not stable, why it is stable, and if it is not stable, why it is not stable. So you have to explain these things. That first you will say that, sir, if this is a negative feedback system, that means I will already get 180 degree phase shift. From where you will get 180 degree phase shift? From here I will already get 180 degree phase shift, and if my loop gain is providing me another 180 degree phase shift, that means my total phase shift will be 360 degree. So at this point my total phase shift is, at this particular point my total phase shift is 360 degree around the complete loop. Around the complete loop my total phase shift is minus 360 degree. Now I need to check at this point if my system is having the loop gain lesser than 1 or greater than 1, because if it is having lesser than 1, then oscillations will die down. So if it is having lesser than 1, that means my system is short stable. That's it. So these kind of questions can come in your examination. What else can come, that we will check. Okay, so let's see two terms. So these terms are used sometimes. Gain crossover frequency. What do you mean by gain crossover frequency? The frequency at which gain is equals to 1, gain is equals to 1 or 0 dB, frequency at which the gain is equals to 1 or 0 dB. So this is your omega gc. And what do you mean by phase crossover frequency? The frequency at which phase shift is 180 degree or minus 180 degree. So phase shift is 180 degree or minus 180. Ideally this is your omega pc. Omega pc is infinity, right? The frequency at which your phase shift is minus 180 degree. So this is known as gain crossover frequency. This is known as phase crossover, and this is known as gain crossover. Okay, let's see some more interesting points. Stability condition we will check. So these two curves are given, like this body plot can come from anywhere. It could be from this point or any point. So this body plot we haven't drawn. This phase plot I haven't drawn. Here also I haven't drawn any body plot. Here also I haven't drawn any phase plot. So this is our system A. This is our system B. So these are very important interview questions. Okay, in a very good interview you will be asked these kind of problems. Now my question is, tell me whether this system is stable or unstable, or oscillatory, sustained oscillation is there, oscillations will die down, or comment on this. Tell me. So how will you comment on this? You will say that, sir, if they will be giving that considering negative feedback system. Okay, they have given considering negative feedback system. So 180 degree I am already getting, sir. Another 180 degree I am getting as this frequency, at this frequency. So at this frequency, sir, I need to check whether my loop gain A beta is greater than 1, less than 1, or equals to 1. So I got to know that, sir, at this particular frequency my loop gain is equals to 1. What does that mean? The system is oscillatory, sir. System will have sustained oscillation. And if there is sustained oscillation, that means this system is unstable. Sustained oscillations. So the system is unstable. That's it. This is how you need to comment. Now, sir, on this condition, from the negative feedback, I am already getting minus 180 degree phase shift. Here, another 180 degree phase shift is there. That means total 360 degree phase shift. So at that point, I need to check what is my loop gain. My loop gain here is greater than 1. If my loop gain here at minus 180 degree phase shift, that is greater than 1, what does that mean? That means there will be oscillations that keeps on increasing. So if there will be oscillations, that means it is an unstable system. Tell me, what was this point? This point was omega gc, right? And what was this point? This point was omega pc. What was this point? At the point where your frequency, omega pc. At the point where your phase shift was minus 180 phase shift. And where was omega gc? This was your omega gc. Okay, why I have put this omega naught? There is no use of this omega naught and all. So this is your omega GC. What did you get to know here? That here your omega GC is greater than omega PC, right? Here omega GC is equals to omega PC. Omega GC was greater than omega PC. This was some lesser value, this was greater value, right? Let's see this condition. Sir, 180 A beta is equals to minus 180 degree I need, because from negative feedback I am already getting 180 degree. That means at this frequency I need to check what is my loop gain, and at this frequency I am seeing that my loop gain is lesser than 1. My loop gain is lesser than 1, and this was my omega GC, and this was my omega PC, and this was my omega PC. So when my phase shift is minus 180 degree, at that time my phase shift is lesser than 1. That means this system is stable. Stable system. So this system is stable. This was your omega GC, this was your omega PC. So what did you understand here? Your omega GC is lesser than omega PC. In this case, in stable system, when the system was stable, in that case your omega GC is lesser than omega PC. In other cases, omega GC was greater than omega PC, and here it was equal. So for a stable system, your omega GC should be lesser than omega PC. You don't need to mug it up, okay? If you want to mug it up, you can mug up, because G is less than P, that's it. G comes first, no? A, B, C, D, E, F, G. So G is less than P, then if you are following the rule of nature, then you are stable. In that manner you can remember, but do not remember it as gain margin and phase margin. Omega GC and omega PC. What is gain margin and phase margin? We will study about it. No need to worry. But just remember that G is less than P, so you have remembered as omega GC should be less than omega PC. Okay, not gain margin, phase margin. We don't even know what is gain margin, phase margin. Okay, those who know, they may get confused sometimes. Okay, sir, gain margin is less than phase margin, system is stable. Absolutely wrong. There is no relation in that. Okay, but if your omega GC is less than omega PC, then your system is stable. There are a lot of exceptions here as well, but whatever that I have told, that negative feedback system, phase shift minus 180 degree, if all these conditions are combined and then you say that omega GC is less than omega PC, then 100% your system will be stable. Okay, but in control systems we can design different kind of system, we can write down different kind of transfer function, then we have to check the stability with the lot of concentration. So when we study control system, you will understand that these formula may go wrong sometimes, because there will be positive feedback system as well, there will be negative feedback system as well, there will be n number of things. But practically, if we have seen some system like this, practically we have designed a transfer function, or you can say a system we have designed. So based on that, we can conclude that if my omega GC is less than omega PC, my system is stable. So let's just revise whatever that we have studied in last half an hour. So first we studied when we can, in positive feedback, what is the condition when we can have a oscillatory system. So in negative feedback, already 180 degree phase shift you are getting from here. Then if your loop gain is also giving an 180 degree phase shift at a particular frequency, then that can be an issue. So for that you need to check the gain at that particular frequency. If your gain is greater than 1, then the system will be unstable or equals to 1. If it is less than 1, then the system will be stable. So then we saw the example of negative feedback. Then we saw the example of a second order system. So this is the open loop. Then we can connect a feedback as well. We can connect a feedback as well. So feedback factor beta we have considered equals to 1, and loop gain is AS is this much. So A beta will give you the phase shift of this much, and the gain would be GM1, GM2, R1, R2 into beta, right? So this is how your body plot will look like. Then we got to know that at infinity frequency we will get phase shift equals to minus 180. So certainly your gain will be lesser than 1. If your gain is lesser than 1, then certainly the system is stable. Okay, so the system is stable, and this is the gain we were having. Okay, so yeah, this is what we have studied. Then we studied the two definition of omega GC and omega PC. Then we analyzed different kind of waveforms. These kind of questions can come in your examination. They can ask you whether the system is stable, oscillatory, or it will have sustained oscillation. Okay, so let's stability analysis of first order system. Okay, let's do the stability analysis of first order system. Then we will do the third order. Okay, so now let's do the stability analysis of first order system. So this is your A beta S. Okay, A beta S, A beta. Gain A is also there, and beta factor is also analyzed. Basically, this mode of A beta you will be writing as K by under root 1 plus s omega square tau square. This is your mode of A beta, and angle also you can write. So better we should write the angle. What will be the angle? Or better we just should write the pole. So only one pole is there, that would be minus 1 by 2, right? Minus 1 by 2. So basically, can you draw the body plot? Yes, I can draw the body plot. This is your gain in dB, and this is your frequency. And then can you draw phase plot? Yes, I can draw phase plot as well. This is how I will be drawing the phase plot, right? So what will be the maximum phase shift you will get in first order system? At omega equals to infinity, you will get minus 90 degree, right? What is the phase shift? What is the phase shift? That is minus tan inverse omega 2. So if you put omega equals to infinity, you will get minus 90 degree, or you also know the rule as well. This will be your minus 90 degree. This is minus 45 degree. And this is your 1 by 2. Tell me if it is stable or unstable. It is 100% stable, right? 100% stable. Why? Because A beta can never give you 180 degree phase shift. A beta can never be equals to minus 180 degree. It can never ever give you 180 degree phase shift. Then how will your total phase shift become 360? It will not become 360, right? The total phase shift will never become 360 degree. That means it will always be stable, right? Always stable. Always stable. 100% stable or always stable. So this was the analysis of first order system. So a first order system, practical first order system. Again, practical first order system is always stable. So always we should design first order system because it is always stable. In a negative feedback, a practical first order system will be always stable. So we should always design first order system only, right? No. Why? Because gain will be lesser, no? This is my first order system. I could have taken an example, common drain amplifier. Here I am collecting the output. Gain is 1, very less. Phase shift from A you are getting 0, and there will be parasitic cap as well. So let's just say there is some parasitic cap. So this transfer function you can get. This transfer function you will be getting. So here I will get a pole, here I will get a 0 as well actually. So this is not a good example. We will get a 0 as well, but forget about it. We will draw the body plot, and certainly you are not going to get a 180 degree phase shift, minus 180 degree phase shift. So you should design this system always when you need the gain. No, because gain will be very less than, very near to 1 or lesser than 1 it is. So for higher gain we need to increase the stages, like 1 stage, 2 stage, 3 stage, and if you increase the stages, then phase shift will increase, and if phase shift increases, then you can go to instability. So as per your requirement, as when you go as a designer, you need to consider how much stage I can add up, how much phase shift I will get. You will draw the body plots, you will check the frequency response, like this is the frequency response only. You will draw the magnitude plot, you will draw the phase plot, and then you will see at the frequency when I am getting minus 1 degree phase shift, at that time what is my gain. So will it be stable or not? So these kind of things you need to check as a designer. So just a simple example I am giving you. Okay. So let's study about the third order system. It will be more interesting for you. So I have given that tau 1 is very greater than tau 2 is very greater than tau 3. That means R1 C1 is very greater than R2 C2 is very greater than R3 C3. That means what will be your first pole? First pole will be 1 by R1 C1. What will be your second pole? Second pole will be 1 by R2 C2. And what will be your third pole? Third pole will be 1 by R3 C3. Right? Okay. So let's draw the body plot. So you will be able to draw the body plot both for magnitude as well, for the phase as well. For magnitude you already know. For magnitude it is very easy. First one roll off is there, then another roll off is there, and then another roll off is there. This was your 1 by R2C2 and this is your 1 by R3C3. Okay, this is A beta only. This I have written complete A beta. Forward gain and the feedback. Forward gain and multiplication with the feedback. What I will get here, that I have written. What I get here, that I have written. Okay, which is K upon S to 1 like this, and this will be 1 by R2C2, and these you know minus 20 dB per decade, and I don't need to write it, right? Minus 20, minus 40, minus 60. And this is the phase plot. So first we will be starting with R1C1. So all the parts will come from 0 to minus 90. Then R2C2 will come. Minus 90 was already there. Minus 90 plus minus 90, that would be minus 180. And then this part would come, another minus 180, another minus 90. So total will be minus 270, right? Now at minus 180 degree, what is your loop gain? There you go. That's it. Here your loop gain is greater than 1. What does that mean? The system is unstable. Now some people will have a doubt. What is the doubt they will have? That sir, what if this particular gain K, this gain K is very low, very low. If that is very low, then your this graph will start from here. This will not change. Why this will not change? Because your phase shift doesn't depend on this value. Your phase shift will be minus tan inverse omega to 1, minus tan inverse omega to 2, minus tan inverse omega to 3. It will not depend on this value. So what if sir, it starts like this. First roll off, it goes like this. Okay. Second roll off again goes like this. Third roll off again goes like this. Not looking very good. So first roll off like this. Second roll off like this. And third roll off like this. So at at this particular frequency, I will have a gain lesser than 1. So my system would become unstable. So yeah, it may happen. But generally your K will be higher if it is a third order system, because you have cascaded 3 stages. So generally as a designer you think, if you have cascaded 3 stages, the gain will be higher, no? So even if there is roll off, there is very high chance that at this particular frequency, it would be somewhere in between. At this particular frequency, there is very high chance that your A beta will be greater than 1 and your system will be unstable. So in third order system or greater, that means third order, fourth order, fifth order, sixth order, there is very high chance of instability. That's why you cannot just keep on cascading the stages. That's why we go to cascade amplifiers, all these kind of amplifiers. There we are not cascading. We are cascading there. By using the current source, we are increasing the gain. Somehow we are increasing the gain. Otherwise, why would you need cascade amplifiers? You just keep on cascading. Just keep on cascading the stages. Then why do you need a cascade amplifier? If you keep on cascading the stages, there is very high chance that your circuit can go into instability in case of negative feedback. So that's why we cannot keep on cascading. We need to use some cascade or some other technique. Okay. So for a system greater than third order, there is very high chance that your system can go into instability. And for lower order system, for first order and second order, you will get lesser gain. So if your requirement is getting lesser gain, then it is fine. Use first order, second order. But if your requirement is getting higher gain, also the stability, then go into some cascade. See the cascade biasing. How will you bias the current mirror? So generally, we do not design any system greater than second order. Okay, so that is very high chances that it can go into instability. So that's it. That's it about your complete chapter. Okay, we will see a few more things if that is required. So yeah, here you got to know that your system is unstable. And the doubt that you could have that, sir, what if the gain was very low? Then yes, you will get a stable system. Then if your gain is low, then why you are using 3 stages? Use only 1 stage. No, if you want lower gain only. So for lower gain, use only 1 stage. Why you are using MOSFET again and again? It will just consume your power. So better use one stage only. So in 3 stages, there is very high chance. If you are using 3 stages, that means you are having very higher gain. And if you are having very higher gain, that means the roll off will be very less till it reaches minus 180 degree phase shift. And at minus 180 degree, you have very high chance to have gain greater than 1. So that's it. So what did you understand? Stability. analysis of first order system. This we have already seen, right? This we have already seen. Let's just remove it. First order system we have already seen. So what you have studied? For the stability, first order have the best stability, then the second order, and then third order. And for the gain, certainly third order will have maximum gain, then the second order, and then the first order. So first order is someone like he is efficient, but he works very low. In a day, he can solve only 10 questions, but he will solve those very efficiently. But this guy, third order, in a day he can solve 50 questions, but there is very high chance that he may do error in a lot of problems. So here the things will be error free, he will be stable, but lesser things will be there. But he will be solving more things and he will be less stable. So better we should go with the second order, because he is in between both of them. But yeah, as per your design, you will decide whether you want to go with the second order or first order or third order. Okay. So yeah, so all the advantage, disadvantage, how we are going to analyze everything we have seen. Sometimes this term is also used, that is phase margin. So what do you understand by phase margin? So this is the formula, but why this formula came, what is the meaning of that? Let's understand that. So let's go to this example. Let's go to this example. So what I have written there, my phase margin is angle of GH omega GC plus 180 degree. This is my phase margin. So when at this was your omega GC, at that time what was your angle? At this time what was your angle? Somewhat lesser than minus 180, right? I can assume the angle is minus 170. Then minus 170 plus 180, that means 10 degree you are having. That means you have margin of 10 more degree until your system becomes unstable. You have phase margin of 10 degree until your system becomes unstable. Because if your phase shift goes by 10 degree more, that means your phase shift are something x, and if it goes down by 10 degree more, it was minus 170 and it goes down by 10 degree more, that means your system would become unstable. So it shows how much margin you are having. Okay. Let's check in the previous examples. Here in this example, this was your omega GC. What was your angle at omega GC? That was minus 180 degree. Angle at omega GC, that was minus 180 degree phase shift plus 180. That means you are having 0 degree margin. Basically, you are at the edge of instability. You have 0 degree margin. This is your phase margin, right? In this case, this is your phase margin. So you are at the edge of instability, right? And what about this one? This was your omega GC, right? This was your omega GC. So at omega GC, you would be having somewhat lesser than 180, right? Somewhat lesser than 180, minus 180. So at omega GC, what you are having? Minus 190, let's just say minus 190 plus 180. So you have a margin of minus 10 degree. That means you have to increase 10 degree. Your phase shift, whatever the phase shift you are having, that should be increased by at least 10 degree. So, so that you go to the edge of instability. So if your phase margin is negative, that means your system is unstable, and if your phase margin is positive, your system is stable. So for practical negative feedback systems, if your phase margin is greater than 0 degree, system is stable, and if your phase margin is less than 0 degree, your system is unstable. And that we have already studied. How much phase margin you have? What does phase margin show? How much margin of the phase you have for the stability or instability, right? So these kind of terms are also used. And as a designer, how much phase margin I will keep? As a designer, I will try to keep 60 degree phase margin. Okay. Once you go into the industry, it depends on the requirement of the project. But as a designer, if I am designing an amplifier, I will try to keep 60 degree phase margin. That means at minus 120 degree only, I should have the gain 1. This angle, this should be minus 120 degree. Okay. Here in the phase, this was the angle plot, this was the phase plot. So here when I am going 0 dB, at that time this should be minus 20 dB, minus 120. So at angle of GH omega GC. So I will try to keep this thing. It depends on the requirement. If they are saying that phase margin you need 70 degree, that means you need to keep this thing. So you have to design the amplifier in that manner. Okay. So I hope you must have understood the complete analysis of stability. So this was the analysis of stability. A good question may come up in your examination from this particular topic. Okay then, thank you very much.